Good morning. Got a new book. I'm very excited. Introduction to Manifolds by Loring W. 2. It was recommended to me by several nice commenters. And one of the things you notice immediately, it doesn't say an introduction to manifolds for scientists and engineers. This is a math book. This was written by a mathematician and it's for mathematicians. So it is deep, deep, and wide. Now, luckily for someone like myself who doesn't do math speak yet, he gives a list of notations and he tells you a one liner of what they mean. He tells you what page they're on. This is a Rosetta Stone for me. Without this, I couldn't even read this book. But okay, I haven't done enough in this that I understand to give a review. And that's not the point of this video anyway. The point of this video is that I found in here something I've been studying in geometric algebra, the wedge product. And the wedge product gives you a differential form. And I don't know what a differential form is. So it says the product is the wedge of two one forms. It gives a two form. Well, I don't know what a one form is, let alone a two form. So that's where I had to start. So that's what this video is about. What is a differential form? Okay, so from my new book, before I can understand what a two form is, I needed to understand what a one form is. Well, it turns out I did know what it was. It's just called something different. So in linear algebra, you have a row vector. In tensor calculus, you have a covector, which is the vector component with a covariant component and a contravariant basis vector. And in differential geometry, they're writing this. So this is the derivative of the coordinate and a covariant component of the vector. They call this a one form. So all of these are very similar in different manners. Okay. What do? Well, in linear algebra, the inner product of a row vector and a column vector yields a scalar. We've all done this before, right? So a row vector times a column vector just gives a scalar. The components of a row vector and the components of a column vector. In tensor calculus, the inner product of a covector and a vector yields a scalar, right? So we write it as this. So here is my vector. Here's my covector. You bring the scalars out front. And this is a basis vector inner product with its reciprocal, or a basis vector inner product with the dual basis of the vector. Either way you want to say it, gives a Kronecker delta. And I has to equal j, or this is 0. And if it's 0, we have nothing. So the j gets absorbed and we're left with the scalar. In differential geometry, the inner product of a one form and a vector, and this vector now is on a tangent plane at a point on a manifold. That's what this means. So it's a vector on a tangent plane at a point on a manifold yields a scalar. And they write the basis of the vector as the differential of the form. So as an example, this would be the partial derivative of a position vector with respect to a coordinate is a basis vector. It's the same thing, right? So we pull the scalars out front. Order differentiation doesn't matter. Once again, this has to equal 1 or 0. And if it's 0, there's no point going. So the j gets absorbed again, and we're left with a scalar. So all three of these things basically do the same thing. They act on a vector and return a scalar. All right. Well, what's a two form? Well, the two form, dxi wedge dxj, takes two vectors and returns a scalar. All right. That's good. So I made up two vectors here. They're very imaginative. 1, 2, 3, and 3, 2, 1. All right. Now they would write these like this. So this is the differential, the form of the basis vector. So this is actually defined as that, right? And so a two form dx wedge d3 as an example, acting on v and u. They write it like this. Acting on v and u. And then they go through the process. They, I meaning, when I say they, I mean mathematicians. So they're saying D1 acting on vector V, they write it out like this, and you can see that the only thing in here that has a component of 1 being differentiated with respect to 1 is this one. These are 0. So you just get 1. And if you do dx1 on u, same thing, you get 3. dx3 acting on v, you just get, this is the only one that's non-zero, you get 3. And dx3 acting on u, once again, the only thing that's non-zero is this, you get 1. So now we've got these 4 scalars. And here's how they write this equation. dx1 wedge dx3, this 2 form, acting on vectors v comma u, they take dx1 acting on v times dx3 acting on u, then they add that to dx3 acting on v and dx3 and dx1 acting on u. So it's really odd the way they do this. It's almost like a commutator. I'm not really sure what to make of this notation, how they do this, but they do. All right, now since these are wedged the products, I can invert these and pick up a negative, and then I have these 2 things in common, right? So I can factor that out. And we know what all these are. We know what the numbers are because we did them above. So we get a -8. So it's like, okay, kind of anticlimactic. I got an 8. What do I do with it? Well, I found out a much simpler way to do that because I've been studying a little bit of geometric algebra. So if I just wedge vectors v and u, and remember the rules, a vector wedged with itself is 0. So we should get 9 terms here when we distribute this, right? But we're only left with 6. Now, we want to combine as many terms as we can, and remember that E1 wedge E2, and here's E2 wedge E1. If I flip this, the 1 for the 2, I just pick up a negative. So then I can add 2 to a -6. And that's what all this is, all right? So there's a -4. Here's an example. I got a 1, 3. Well, here I got a 3, 1. If I flip this, I got a 1, 3, and that becomes a negative. So it's 1 plus a -9 is -8. So I get these 3 things. Now let's convert that back to differential, the form speak, and we get this. So you can pick right out of here all 3 of them. So the dx1 wedge dx3 is 8, which we got. dx1 wedge dx2 is -4. And the reason you're getting negatives here is because the way I chose to wedge these, I'm wedging v with u, and so I'm getting a clockwise rotation on this bivector, which makes it a negative. Now, let's go look at what are we doing here? What is this stuff? Okay, so here's our handy dandy 3D Desmos graphing calculator. I think that's what they call it. Desmos.com/3D. So we have 2 vectors, okay, v and u. Now, when I wedge these 2 together, it forms a bivector. So a bivector is an oriented plane, right? So a vector has direction and magnitude of a line. A bivector has direction and magnitude of a plane. And its direction is what I said before. I'm wedging v with u, so I'm getting a clockwise rotation, which makes it, their position is it's negative. If I wedged u with v, I get the opposite. I get a counterclockwise rotation, and they call that a positive. All right. So they're anti-commutative. Anti-commutative. Yes, that's the right word. All right. So what does it mean, a 2 form acting on this? What exactly is it doing? Well, if you can imagine shining a light from above, on this, the projection of that on this plane, xy plane, would be the two form of dx1 and dx2, right? And it would look like this. All right. So let's line these up. You see? So that is the projection of that bivector on the xy plane. Now, what about on the xz plane? Well, it's the same thing. It's the projection of this bivector onto the xz plane. So that is the two form dx1, dx3 is this one. And there's only one left, which is the YZ plane, and it looks like that. And you can see when I line them up right, the YZ plane, it's the shadow of that. So these two forms are the projection, the shadows in these three different planes. And they have those values that we found, which is 4, 4, and 8, which we saw in the document. So what do you do with them now? I don't know. Just went through step one. All right, see you later.